When we're working with solutions, we often come across a problem that we may have obtained a solution that we just don't know the concentration of. Luckily, there is a lab technique that is used in order to solve this problem. This technique is called a titration. And a titration is just essentially practical stoichiometry. It's using the principles of stoichiometry in order to find the concentration of some dissolved substance. In order to do a titration, you need a little bit of specialized equipment. So you need to have a titration setup. Usually what that is made out of is something called a burette, which is often a large glass or sometimes plastic tube, and it measures volume on it. It has a thing that's called a stopcock, which is able to allow very specific amounts of liquid in and out. The burette is designed to measure volume. So it is then added to a solution that is in a flask. Specifically, it's in what's called an Erlenmeyer flask. And by mixing the two in this flask, a reaction then takes place. A titration is usually done between an acid and a base. And as I said previously, it's designed so that we can actually do stoichiometry in order to find out the concentration of a substance. So let's take a look at an example where we might see this. So an example of a titration might be taking the substance sodium hydroxide. Sodium hydroxide has the property that it absorbs water out of the air. So if you make a solution of it, you actually don't know the concentration. It's really similar to like brown sugar. Brown sugar gets really, really hard because it's absorbing water moisture out of the air and becoming a solid block. If you were to put that on a scale, you would actually end up weighing the water vapor and the sugar, and same thing if you were to do this with sodium hydroxide, you would weigh the water and the sodium hydroxide. That ultimately means that you can't just weigh it to find moles, you have to do a reaction to find moles. And this would then be reacted with an acid. So let's say HCl. When they react, they produce water, and in this case, it literally is table salt, but it always creates something that we call a salt because it is a binary ionic compound. So we often have a base, and a base is just a substance that has OH at the end, for now anyway, until we get further in the course. And then HCl is an acid. They will always react to make water and a salt. This is essentially the chemical reaction that we undergo every single time that we do a titration. Maybe not exactly these substances, but you use a base, mix it with an acid, it'll make water and some kind of salt. Maybe not NaCl, but that kind of depends on what you have here. Now, because this is a double replacement reaction, you have two aqueous reactants. You have a liquid in the form of water, and the salt, you would check your solubility table, but in this case, is aqueous. Now, the reason we can do a titration is because of the way we set up our equipment. In the burette, we would include the substance that we know the concentration of really, really well. That, in this case, might be like our HCl. This is what we would call a standard solution. And a standard solution is one where we know the molarity. You can then also measure a specific volume. And this is going to give you the moles. Remember, moles is equal to molarity multiplied by liters. By using the burette, we can actually measure the volume of the acid or of the standard solution that we would add. We would also pick a solution that has a really well-known concentration. From that, I know the moles. Once I know the moles of one substance, I can actually use stoichiometry to find the moles of another substance. So I could use stoich to find out the moles of NaOH. Now, if I know the moles of NaOH, I can actually use this to determine the molarity as long as I know the liters. And this is actually really easy to do because you would just measure an amount. You would actually just take an instrument, measure how much you would use. That would give you your liters. Stoichiometry would give you your moles. And remember that the molarity is the moles divided by the liters. So you can see it's actually just a practical system for using stoichiometry. And because of this, we can end up doing calculations that lead us to finding concentrations or volumes or whatever it is. And because it is just stoichiometry, that's all we're going to do inside of our calculations. So let's work through a couple examples so that we can see how you would do this. So in this example, what volume of 0.32 molarity nitric acid is needed to neutralize 26 milliliters of 0.22 molarity calcium hydroxide solution? So in order to do this, we need to follow our steps for stoichiometry. So number one, balanced equation. So my balanced equation is going to be nitric acid, HNO3, which is aqueous, reacting with calcium hydroxide, CaOH2, also going to be aqueous. They're going to react to produce water because an acid and a base always produce water, which is a liquid. You cannot have aqueous water. That's water dissolved in water, which is just water. And then calcium nitrate is going to be the other product here, and it's going to be aqueous. Now we need to balance. So I have two NO3s. I need two NO3s. That gives me two H's plus another two H's. Gives me four H's. So I need four H's. That gives me two O's, and I have two O's. So that is my balanced equation. Let's fill in the information that we know. So we have 0.32 molarity nitric acid. It's asking us what volume of nitric acid do we need if we have 0.22 molarity calcium hydroxide and 26 milliliters, which would be 0.026 liters. So we have our balanced equation, we've sorted our information, and now we need to go to moles. So using our molarity equation, we are going to take the molarity and the liters and convert it into moles. So 0.22 molarity for calcium hydroxide multiplied by 0.026 liters of calcium hydroxide. What this gives you is 5.72 times 10 to the minus 3 moles of calcium hydroxide. So that is now my moles. So now I can use my molar ratio. So I have 5.72 times 10 to the minus 3 moles of calcium hydroxide. And I want to figure out, okay, how many moles of acid is that? Because we need to find liters. And so that means we need to get moles so I can use my molarity equation. So now what I'm going to do is take moles of HNO3, put that on top, moles of calcium hydroxide, put that on the bottom, and then I'm going to use my molar ratio, which is from my balanced equations coefficients. And that is going to give me how many moles of HNO3 would react with calcium hydroxide. Now that I know the moles, and I should put moles. Now that I know the moles of HNO3 that would react, I can use my molarity equation to calculate liters. So liters would be moles divided by molarity. So that's going to be 0.01144 moles divided by 0.32 molarity. And you should get an answer of 0.035, and actually we need to round this to 36 due to significant figures. Oh, and that should be liters, sorry. Now, 0.036 liters is kind of an awkward way to look at this. So you could round or change your units to 36 milliliters if you wanted to. One thing that we should talk about too is when you have this kind of reaction, the acid is normally clear and colorless. Even though I know on like cartoons they look like they're bubbling and green, they're always clear and colorless. Bases dissolved in water, clear and colorless. Water, clear and colorless. Salt dissolved in water, clear and colorless. In order to actually get this reaction to work, you need something that's called an indicator, because an indicator will change color when you have the correct amount of moles. This is what we would call the end point. It's when we end our titration, when our indicator flips and changes color. Good examples would be like phenolphthalein, that is clear and colorless in an acid, that turns bright pink in a base. So as soon as you see it turn to a pale pink color, you would actually know that you finished this titration, and then you would be able to do your calculations. Now that we've gone through one example, maybe let's take a look at a second example and see how we would do that calculation. So what's the concentration of 10.0 molarity, of 10.0 milliliters of KOH if 15.0 milliliters of 0.65 molarity sulfuric acid is needed to neutralize it? Okay, so we are just going to go through the same steps. We're going to do a stoichiometry problem. I should mention here, if you're really adept at chemistry, you're going to notice that we're cutting a corner here. And if you're just new to chemistry, don't worry about that. This is going to be good enough for what we're going to do. So we're just going to work through this using stoichiometry. So we have our balanced equation, which is potassium hydroxide reacting with sulfuric acid. They're both going to be aqueous because it's double replacement, and they're going to make water because it's an acid reacting with a base. Water is a liquid, and they produce a salt, which is going to be K2SO4. That's going to be aqueous. Water is a liquid. These two are aqueous, and there is our equation. We then need to balance it. So I have 2 K's over here. I need 2 K's over here. That gives me 2 H's plus another 2 is 4. So I need 4 H's. That gives me 2 O's. I have 2 O's over here. It's asking us what is the concentration of KOH if we use 10.0 milliliters, equivalent to 0.0100 liters. And it took 0.65 molarity sulfuric acid, and it was 15.0 milliliters, equivalent to 0.0150 liters. Okay, you can see we were given enough information here to calculate moles. So moles is molarity multiplied by liters. So 0.65 molarity multiplied by liters, so 0.0150 liters. That tells us that we have 9.75 times 10 to the minus 3 moles of acid of H2SO4. Now we're going to use our molar ratio. So 9.75 times 10 to the minus 3 moles of H2SO4. We're going to convert that into moles of potassium hydroxide. So there are 2 moles of potassium hydroxide for every 1 mole of sulfuric acid. That gives us 1.95 times 10 to the minus 2 moles of potassium hydroxide. Now that we know how many moles of potassium hydroxide we have, we can calculate molarity. So molarity is just moles divided by liters using our formula. And so it's going to be 1.95 times 10 to the minus 2 moles divided by the volume, and it has to be in liters. So 0.0100 liters. And we get a concentration of 1.95 molarity, and we need 2 significant figures due to the 0.65. So this is actually going to round to 2.0 molarity.